send me an email. I'll be glad to post it or give it to you via email. So, all right. So we got two big ideas that I want to do today for section 4.2. We want to work on something called sigma notation, whatever the heck that means. We're going to do sigma notation. And then this part right here, use the limit definition to calculate area. I'm not going to sugarcoat it, guys. This part here is tough, okay? This is going to be the tough part. This is going to be, if you remember on that first slide that we had when I talked about going from the shortcuts back up to the formal definition, if you will, that's what this is going to be, okay? This is where we're going to have to deal with some heavy-duty mathematical stuff. But anyways, let's start with sigma notation. So this right here, that is sigma notation. And we call it sigma notation because guess what that symbol is? Sigma. It is the Greek letter sigma. Turns out there's a capital sigma, there's a lowercase sigma, this is the uppercase sigma. And just in case you're curious, oops, I'm still on the eraser. Lowercase sigma is that, we actually use that for something called standard deviation. Anyways, so this is our uppercase sigma, and all it means is add. It means add. Add whatever this stuff is. So let me give you the easiest example of, or one of the easiest examples that I can think of. Let's go to 4, and then I'll just say that this is, we'll call that I. Now, all I is a variable, and it gives us the rule that we're going to use here. And so what we're going to do is we're going to start at 1, and we're going to go up to 4, and we are always going to use our natural numbers here. So we start at 1, we're going to go to 4. So here's what this is telling us. The first I is 1. So I put 1 in for I. Plus, because that's what this is a summation. What's the second I? 2. Plus, can you guess what the third one is?
3 for 100.
3. And last but not least, because we're going to stop at 4, guess what the last one is?
4.
4. So our sum here is going to be, I believe, 10, assuming I added those up correctly.
I also got that.
Because 1 plus 2 is 3, plus another 3 is 6, plus 4 more is 10. This is sigma notation. In fact, this is the sigma notation that represents this sum. Okay? Now you might say, Mr. Round, that seems like that wouldn't have been very hard for me to do that, right? Just write 1, 2, 3, 4, and then add them together. Okay, what if instead of going from 0 to 4, what if I said go to 4,201 or 21?
I think that's a little bit tricky.
It's a little bit more work, isn't it?
Yeah.
Or better yet, let's throw on 3 more zeros. 4,021,000. Now, if you wanted to, technically, you could write all 4 million of those out, or you could just very compactly write this notation. Does that kind of make sense why that's helpful?
Yes.
Instead of having to write all 4,021,000 of those, I could just write this little thing here. And by the way, this is going to be a very big sum, but we're not worried about that. My point is, it is a nice, compact way of writing an addition. So let's look at a couple of these. We're going to do these sums, and we're going to verify them with a calculator. So hopefully you brought your calculator today. If you guys are in virtual land, hopefully you guys got your calculators. Now I'm going to just rewrite this first one because for whatever reason, PowerPoint wouldn't let me write it quite the way I wanted to. So this is the summation from J starting at 4 going to 6 of 3 over J. Here's another equivalent way of writing that. Now you'll notice that, wait a minute, Mr. Allen, you're using a different variable here. Guys, does it matter what letter is there? Nope. Not really. We usually use I or J or K. Typically for the indices, we'll use I, J, or K. We'll use one of those 3 letters, but we can literally use any letter. We usually avoid C and A, but anyways. So here's what that means. If I expand this, it just means if I write it out. We start at 4. Now, notice I didn't start at 1. You usually start at 1, but you don't have to start at 1. Here, we're going to start at 4. So this is going to be 3 over 4. That's the first one. What would the next one be? 3 over 5. What about the next one?
3/6.
3/6, or 1/2, right? So here is our sum written expanded. Now to find this sum, we're going to have to get a common denominator, right? So let's see if we can actually sum these up here. And I'm going to go ahead, if you guys don't mind, I'm going to kind of write this in a little bit easier way there, because 3/6 is the same thing as 1/2, right? What is the least common denominator here? I think 20, isn't it?
Yeah.
Isn't it 20? So if I write all of these over 20, and by the way, the purpose of this lesson today isn't to do arithmetic, even though we will be doing a little bit of that. We'll actually be doing more algebra than arithmetic. We got to do a little bit of arithmetic here. So let's see, I'm going to multiply the top and the bottom of this one by 5. So I think that's 15. This one by 4. So I think that'd be 12. This one by 10. So I think that'd be 10. Denominator stays the same. So 20, I think it's 37 over 20 if I'm not mistaken. Would you go ahead and try B? This one's a little bit more work. Okay, well, you guys are working on this sum. I'm going to start showing a little bit of work. Okay, so hopefully you kind of figure this out. When we expand this, it's just one less than the next perfect square, right? So you got the first perfect square minus 1, so that's 1 minus 1, so that's a 0. 2 squared minus 1, that's 4 minus 1, that's 3, and then on down the line. So the next perfect square is 9, so it's 1 less than 9. The next one's 16, 1 less. Anyways, and so when you add these all up, again, if I'm not mistaken, I think you get 375, okay? 375. Now notice in this particular sum, we did start at 1, and in this case, I used the variable I, but I could have used J or K or something else if I wanted to. Would you guys like to see how to do this more quickly with a calculator?
Yes.
So if you have your graphing calculator, get that out. I'm going to use, hopefully I'm going to use the screen up here. Hopefully this doesn't blow up on me. Okay, so I've got my graphing calculator popped up here. And so what you want to do is, well, turn it on, go to math, and then you're going to go all the way down to option number 10. Now, I got to forewarn you, if you have one of the older graphing calculators like a TI-83, it may not work. But if you have one of the TI-84 newer ones, hopefully you do, you'll see it says summation. And I'm going to hit enter. And you'll see that there's a sigma there. And I'm going to go ahead and use the variable x because it's easy for me to put x's in there. And I'm going to let x start at 1. And then I'm going to go up to 10. And then I'm going to do, let's see here, x squared minus 1. And then I'll just hit enter, and you'll see there's the answer, 375. A little bit easier, right? So I hope you can do it with a calculator. That's great. But I also expect you, whoa, I don't want that. Not sure. Okay, good. That went away. Not sure I wanted there. Wow, look at that. Can you see the text now? Right there, look better. Okay, good. All right, I'm learning things. Okay. Any questions so far, guys? So as you guys agree, sigma notation, not a big thing, right? Now we're going to have to keep working with this a little bit more. And here's some rules that I would encourage you to keep reference of. This is also on my presentation notes that is on the Canvas page. In particular, these three, this one's a definite, this one's a definite, this one's probably one. I won't probably ever ask you to use this one. Now, just very quickly, I want to show you what these are these are some common summation formulas that we're going to need. And I'm going to show you the easiest one right here. So let's say that I asked you to do the sum of 2, starting with 1 to, let's say, I don't know, 7. In other words, what I'm telling you to do is to do 2 plus 2 plus, how many 2's am I plussing together? 7 of them, right? Starting from 1, going to 7. So there's 2. So there's 3, 4, 5, 6, and there's 7 of those. Now, guys, it should be pretty easy to see what the answer is.
2 times 7.
2 times 7, right? It's 14. But I could have just used what the formula told me the answer was. The formula just says take whatever C is. This is the C value. This is the N value. So C times N is 2 times 7, which is 14. Fair enough? Now, obviously, that one's pretty intuitive. These others, like, that's probably not too intuitive to you, is it? N times N plus 1 over 2. Let me give you an example of that one real quick. So let's say I said, what is the sum? I starting at 1 to, let's say, I don't know, let's make it 10 of I. Guess how you would find that sum? Well, you would take N, well, what's in here? 10 times, now you got to do N plus 1, so that's 11, all divided by 2. Well, the 10 and the 2 cancel to become 5, and 5 times 11 is
55.
So this is 55. So I didn't list any of them out. I just used the formula. And again, you might say, well, Mr. Allen, I could have just listed out 1 plus 2 plus 3 plus 4 plus 5 plus 12 all the way up through 10 and added them up and got 50. You could. But what if instead of the first 10, I said, what's the sum of the first 5,272? It's actually very simple with this formula. Okay? Comments or questions on this? We're going to use these soon. And again, let me just say this. I expect you to know these two. And this is the worst case scenario I'll probably ever ask you to use on an assignment. I probably will never ask you to do anything to I to the third. Okay, a couple of other things. So here I mentioned the fact that, typically we use I, J, or K. I've already talked about that. But here are a couple of properties that I like to mention. In fact, let me start with this second one here, which is the distributive property. You guys probably remember that 2 times x plus y is equal to what?
2x plus 2y.
2x plus 2y, right? Yep. That's what this is saying basically here. Okay? Think of this out here. If this was 2, and that's x, and that's y, and this is a plus, what would you do? You would do 2 times the x plus 2 times the y. That is exactly what we've done here. Let me erase this part. So what I'm saying is if I have to do this summation of something plus something or something minus something, that just means I could do the summation of the first thing plus or minus the summation of the second. It's like the distributive property for summations. And the other property, this is another one that we've seen with limits and derivatives. By the way, these both apply to derivatives and limits as well, is if you have a constant like 2, you can actually pull it out to the front. In other words, if I said, what's 2, 7, oops, no, I'm not doing it right. If I did the summation of 2i, I starting from 1 to, let's say, I don't know, 10, that is the same thing as 2 times the summation I starting from 1 to 10 of I. So I can pull the 2 out to the front. By the way, that also applies to limits and derivatives. All right, you guys ready? Okay. I'm going to show you how those rules work, and then we'll get to the real meat of today's lesson. Let's say I actually want to find, we already found this answer. What was this answer? Wasn't it, I think it was 375, wasn't it? Yep. Wasn't that what we said the answer was? We did this one. This is the same problem. I just put it up here and I call this example 2. And now instead of listing these out, which we did earlier, right, with 0, 3, 8, blah, 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 I'm going to use these formulas. In fact, I'm going to use both of these formulas. Now, the first formula I'm going to use is that summation formula that we just saw in the last problem, or the last slide, I should say. What was this one called?
The distributive.
Distributive. Would you guys agree that I just did the distributive property?
Yep.
That's what I did. I basically took this to this and this to this. Agreed?
Yep.
Oh, what is the summation of I to 10 of I squared? Well, I could list them all out, or I could just use this formula right here. And remember, n in this case is what? It's 10. So I'm going to do 10 times 10 plus 1, that'd be 11, times 2 times 10 plus 1, that'd be 21, all divided by 6. We'll figure out what that is in just a second. But notice that there's no more summation, and I didn't write a bunch of additions. In fact, this is all multiplication. Minus, oh, and this one's an easy one. What's C?
1,
And what's N?
10.
10. I just use this formula. All right, so now I got to do a little bit of math here. This isn't going to be too fun. Let's see here. 21 times 10. I think that's 210. Now I got to take that times 11. So let's see here. That'd be 210 and then 210. And then add those together. That'd be 2310. And then I got to divide that by 6. 2,310 divided by 6. And that's, of course, that's a 10 here, guys. This is a 0 right there. So now I got to do 2310 divided by 6. Let's see here. 6 goes into that 3 times, I think, right? That'd be 18 with 5 left over. So 51. 6 goes into 51 8 times. Doing this in my head, guys. I'm not trying to impress you, but it is what it is. So then that'd be, what, 3 left over? So 30. 30 divided by 6 is 5. Minus 10. And I get 375. Now, guys, look, you might say, Mr. M, we could have done that like, you're right. I could have even used my calculator. You're right. I just want to convince you that these formulas are true. When I did my master's degree a few years ago, we actually had to derive these formulas. And it was actually, when I did this one, I think it took me about 6 pages of work. Mm-hmm. And I'm not saying that to be like, look at you. I'm just telling you, coming up with these formulas isn't so easy. So the good news is I'm just saying, here they are, okay? All right, so guys, I'm going to start the next example here. But before I do that, I want to show you something, and I want you guys to take a real quick poll, if you don't mind. So those of you guys that are virtual, I'm launching a poll. I'd like you to answer the question. Okay, so far, everyone's getting it right. So they were paying attention. So that's good. Okay. All right, so that gives me a little bit of a segue here. All right, so guys, so up to this point, all I've said is that our lesson is on area. Guess how much area we've talked about?
Zip.
A zero. So now I'm going to try to put it together for you, okay? Now let me go back in time to just derivatives. Derivatives calculate the slope of the tangent line, right? That was the geometric representation of what a derivative is. It is the slope of the tangent line. Now we're going to talk about what is the geometric representation of an integral, the definite integral, which is where we're moving. Guess what it turns out to be? It's not the slope of the tangent line. It's actually the area under the curve. You might remember that all the way back from the beginning of the year. You probably don't, but if you do, awesome. So here's what I've got. I've got this curve. It turns out it's a degree 3 polynomial, and I could change A, B, C, and D and make this look however I wanted. But right now I want you to consider just going from -1 up to 5. I have how many rectangles drawn there?
4.
There's 4 rectangles, correct? And that's why it says n equals 4. Got it?
Yes.
Would you say that if I was trying to find the area under the curve from -1 to 5, would you say those rectangles would kind of approximate? Not very good, but we could say that whatever the area of this rectangle and this rectangle and this rectangle, and those, if I put those together, that area would roughly be the area under that curve. Would you say that's true? Yes, but it wouldn't be very good, would it?
No.
What if I did 5 rectangles, 6 rectangles, 8, 9, 11, let's go up to, let's say 20. Okay, I'm going to stop there. Now, instead of 4 rectangles, I did 5 times as many. So this is 20 rectangles. Would you say that these rectangles, if I were to add up all 20 of their areas, do you think that would be a better approximation?
Yes. Definitely.
Yeah, it'd be better, wouldn't it? Huh. What happens if I did 100? It'd be even better. What if I wanted it to be, here's a very important calculus question. What if I wanted it to be the perfect area?
You have to not confident.
I'd have to do infinitely. I'm just telling you right now, what you're getting ready to see is we're all of a sudden going to jump back to chapter 1 again. Because a derivative is a limit. Guess what an integral is?
Also a limit.
It is also a limit. Okay. Oh, by the way, the shape, what was the geometric shape I used to approximate that area? It was a rectangle, right? Let me see if I got my marker here. Nope.
Well,
Yeah, there we go.
all squares are rectangles. But not
Oh, boy. Come on, technology. I just want to write. There we go. We used rectangles, right? Okay, so here we go. Now, guys, this is the hard one. I'm only doing 2 more examples. But this example is going to take some time. And I'm going to tell you right now, as I go through this example, it's going to seem like a bit much. But remember, I told you last week I gave you the shortcut. This week, I'm giving you the behind-the-scenes look of what's actually going on, okay? So here we go. In fact, I'm just going to start. Can I just give you the formula? I'm just going to write the formula down, and then I'll talk about it, okay? So this is area. It is equal to the limit as n goes to infinity, sigma I starting at 1 to, I almost wrote infinity, but it's going to be n. We're taking n to infinity, right? F of c sub I, that's an I, and then delta x. Holy smokes, that's the formula. Wow. What in the world is that, Mr. Allen?
I have a question.
Yes.
About can the thing under the sigma or the thing, Can it ever be anything besides I equals 1?
Yes.
Does the 1 just determine the value that we increase by?
Typically, it's the first natural number, which is 1.
Yeah.
But there are many instances where it's 0, and we could make it be any positive number that we want. If you get into higher level mathematics, it could even be negative values. But we don't want to talk about that today.
Okay.
All right, so here we go. Let me break down the idea of this formula before we start looking at it. So do me a favor. For a second, just forget about the limit part, okay? Forget the limits there. In fact, I'd like you to forget about this sigma. In fact, I'm going to write this again. You guys don't need to write this, but I'm just going to write this part right here. I should probably put a little dot there because that's times, right?
Yep.
What was the shape that we just used when we talked about approximating the area under that curve?
A rectangle.
We used a rectangle, right?
Yes.
What is the formula for the area of a rectangle?
Length times width.
Do you guys mind if instead of calling it length times width, if I call it base times height?
No.
Is that okay with you guys?
Yes,
Okay. So guess what this is right here?
that's the base.
Nope.
That's the height.
Yes.
Wow.
Think about it. If you draw a curve, like this. Let's just say I got this curve. And let's say that this is the x-axis right here. How do I find this distance right here?
The y.
That's the f of whatever it is we plug in, right? So this is the height of our rectangle, right? Now, if that's the height, can you guess what this is? Delta x.
The base.
It's the base. Base times height. So what I'm basically doing here is this is essentially the formula for the area of a rectangle. It's base times height. Now, in that last thing I showed you, I think we did n was 20, didn't we? There was 20 rectangles. What did I have to do with all the areas of those rectangles? I had to
add them together.
add them together, didn't I?
Yes.
Guess what this does?
It does the thing.
This adds all of those areas. It's literally taking all 20 of those rectangles. It's finding the area of the first one, plus area of the second one, plus area of the third one, plus all 20 of them, correct? Does that make sense? Now, here's the final step. How did I say we get the exact area? How many rectangles did we need?
Infinitely many.
That's where this part comes in. Okay? So this is it in a nutshell. And guys, I'm just going to tell you, after today, I'm going to talk a little bit about this, but today's going to be the hardest part of this. I'm going to focus on this today. We'll talk a little bit about it tomorrow. And then again, I'm going to kind of focus more on the shortcuts, but I want to show you where this comes from. Okay? So now I'm going to erase some of this stuff because I'm actually going to work this out. And I'm going to tell you right now, I'm going to give you a couple more formulas within this, and then I'm going to work it out. The way you'll get good at this, the way that you'll understand this is by doing some problems on your own. So the first thing I want to do is I want to define what x is, or I'm sorry, delta x. Delta x just means the change in x. In this case, x is going from what to what?
0.
So to find delta x, and I'll just give you the formula, it's b minus a over n. So in this case, it's 4 minus 0 over n, or 4 over n. In this example, the change in x, the delta x, is going to be 4 over n, where n is the number of rectangles. And by the way, just to let you know, as n grows large, what's happening to that number?
It's smaller.
Correct. If n goes to infinity, what does that become? Infinitesimally small. Okay, next thing. C sub I. In general, actually I should not say in general, for this class, C sub I is the same thing, just put an I next to it. Now I'm going to just give you a little note for those of you that are really, ambitious. This is only in the case where x starts at 0, or a, I should say. Someone hit a question or something, I think. Okay, sorry guys, I thought I heard somebody type something. Okay.
Yeah, Mr. Allen, that was me.
Okay, did you have a question? Sorry.
Can you just pause for a second? I'm having trouble trying to write everything down.
Okay.
at the same time. And I just want to copy down the CI really quick so I don't miss it.
Okay.
Sorry.
Don't be sorry.
Okay.
Okay, thank you. So guys, now let me just make one more comment about this C sub I. This does not have to start at x equals 0. I'm not sure that I'm going to actually spend any time this year dealing with those situations. So for right now, this is basically all you need to know. Okay. And guys, the only reason I'm showing you all of this stuff is I want you to make sure that you understand the behind the scenes stuff, what's going on with integration. It didn't just fall out of the sky. This is actually how they used to try to calculate it a long time ago before they figured out the shortcuts, which we'll spend more time on. Now, guys, here we go. I am now getting ready to do this problem. And I'm just going to forewarn you, the algebra is kind of ugly, okay? There's a little bit of algebra going on here, but we'll get through it, okay? So here we go. So, and I'm going to do this. Let's do it in black, and I'm going to kind of make a new little space right here. And I'm going to start working with this for this particular problem, okay? So I'm telling you that the area is going to be equal to the limit as n goes to infinity of the summation from 1 to n of f of 4 over ni, 4 over n. So only thing I've done here is where there was that delta x, I changed that to 4 over n. The only other thing I did is see where that c sub I is? I just plugged in 4 over n times I. Oh, one other thing. That I has nothing to do with the imaginary unit that you learned in pre-calc, okay? We're not doing any imaginary number stuff in here. Okay, the next step. Now what I've done is I've got this piece right here. Let me underline it. You see this piece right here where it says 4 parenthesis 4 over ni?
Yes.
Well, what do you got to do with that 4 over ni? You got to plug it in to this. That's what the function is. So I literally took that 4 over ni and I plugged it into this function x plus 3. Now you'll notice over here, I just wrote lim and I wrote the sigma symbol and I didn't write the n goes to infinity and all that stuff. You know, I probably should do that, but I think I'm going to save myself a little bit of writing, and you can as well. Those are going to stay the same throughout the entire problem. There's going to be a couple of times where I'm going to emphasize those, but just to save you all the writing of this stuff, I'm not going to write it on every step. Now I have everything that I need. I've just got to start doing some algebra. So this is just algebra. I'm not actually doing any limits yet. I'm just going to focus on this piece right here. And guess what property I'm going to use right now? Distributive property. Does that make sense? So here we go. So the next step is going to be the limit, summation. And again, I'm not going to write the n and go into infinity and all that stuff. This is going to be what? 16 over n squared I plus 12 over n. All I did is distributed the 4 over n. Guess what I'm going to do now? I'm going to do that distributive property with the summations. So this is going to be the limit of the summation of 16 over n squared plus, oops, don't forget the I, the summation of 12 over n. Now do me a favor, on this step, I do want you to put the n goes to infinity and the I going from 1 to n. I do want that on this step, and I'll explain why in just a second. going to go to the next slide here, guys. I'm going to want to make sure I write this down exactly where we're at. Okay, so we're right there. I wish I could copy and paste that. But guys, I'm going to rewrite. I'm going to go to the next slide. I apologize. I'm going to go to the next slide. I'm going to rewrite this statement again. So if you didn't get it written down, here it comes again. So this is equal to the limit as n goes to infinity, summation I going from 1 to n of 16 over n squared I plus summation of, was it 8 over n? Is that right?
Yep.
Thank
No,
you.
that is 12.
I thought it was
Oh,
12.
12. Okay, sorry. Thank you. Black. 12. And this is all in parentheses, right? This is that last step we just had?
Yep.
Okay. Now here's why I wanted you to write this here and here. Remember, when you have the summation with an index of I, the only thing this summation changes is the I, correct?
Yeah.
It doesn't affect the n. So that means the following is true. The limit as n goes to infinity, I can now consider this 16 over n squared without, because it has, oh boy. Hold on, guys. Sometimes my shirt gets a little bit too close to the projector, and that causes a little bit of a problem. So now notice the following. This summation is 16 over n squared, but it doesn't have an I. So if this had just been 16, you just would have pulled the 16 out, right? Well, the n squared doesn't have an I either, so you can disregard the I part on that as well. So the only thing that's left, let me circle this. This part has nothing to do with I, so I can put it in the front. This part has nothing to do with I, so I can put it in the front. Now, don't forget to put the 1 there, though, right? 1 times 12 over n is 12 over n. Okay. Remember those formulas I mentioned a few minutes ago?
Yep.
We're going to use them now. First things first. So I got the limit as n goes to infinity, 16 over n squared. Now, what was it that we said we could put in here for the summation of I
N plus 1
n plus 1?
over 2.
Agreed?
Yep.
Okay, we're going to use that. What can we put in for this guy right here?
C N.
C times n. Agreed?
Yep.
By the way, in this case, what's C?
1.
C is 1. So let me go ahead and put that in this case. It's just 1 times n or just n, right? So here we go. And I'll do it in purple here just to emphasize that. So this is going to be times n plus 1 over 2 plus 12 over n. Multiply that by whatever we said that was, which I think we said was n. Now, this was a very important step because look what just went away.
The summation.
The summations, which is beautiful because now I don't have to do any sum. In fact, I could have given you this problem right here back in chapter 1. I could have said, what's the limit of this algebraic thing? Oh, by the way, some good news. Guess what happens to this n and that n?
It just becomes 1.
They cancel, right? This cancels this, doesn't it? This 2 and that 16 becomes 8, doesn't it?
Yeah.
Okay, good. So that gives us the following. We need to do the limit as n goes to infinity of 8 times n squared plus n. I went ahead and distributed that n there. Over n squared plus 12. Now I'm doing chapter 1, right?
Yeah.
Now, what about this right here? Do you guys remember that trick where we would divide by the highest power? So divide by n squared, divide by n squared, divide by n squared. Do you remember doing that when we did limits? Yeah. So this is the limit as n goes to infinity of 8 times. Now, what's n squared over n squared?
1.
1. What's n over n squared?
1 over
n. And what's n squared over n squared?
1.
By the way, what's n doing? It's going to
Infinity.
So what's the 1 over n going to become?
0.
A 0. So you're going to get 8 plus 12. So I'm telling you the exact area is under the curve is 20.
What?
Now you're probably sitting there thinking, Mr. Allen, that was way more work than I thought it was going to be. And you're kind of right. Because this problem could have been done much more easily. Would you guys like to see an easier way to do this one?
Yeah.
Now listen, all this stuff here is correct. But I'm going to draw a picture over here on the chalkboard. I'll let you guys, if you're copying stuff down, copy stuff down. Okay, guys, I'm going to move the camera here for a second. I'll bring it back. I'm going to put this on me so that I can actually see. Go. Okay, guys, so what I've done here on this chalkboard is I just drew, here's the function right here. This is the function y equals x plus 3. You guys familiar with that? That's what this problem's all about, that, right? If we go back to the problem, the original problem was f of x equals x plus 3, and we were going from 0 to 4, right? What shape is this?
It's a quadrilateral.
It's a quadrilateral. What kind of quadrilateral? What do we call a quadrilateral with exactly one pair of parallel sides? Called a trapezoid. Do you guys remember the formula for the area of a trapezoid? I bet you probably forgot that, but I'll remind you. It's a half times height times base 1 plus base 2. I don't know if do you guys remember that by chance? Okay. Now remember, the bases are the parallel sides, right? What's the length of this base right here? That's easy. That's 3, right? What about this base? That's harder. If you plug 4 into that, though, what do you get?
7.
So that's 7. Oh, what's the height of this guy?
4.
4, right? Okay, so let's see here. 1/2. Height that's the height, so that's 4. What's the first base? 3. What's the second base? I bet you'll never guess what that is.
Is it 20?
What's 3 plus 7?
10.
Times 4?
40.
Divided by 2.
Oh my God, that's fun.
Now, I'm going to come back here. And you might say, wait a minute, Mr. Allen. I would have done that trapezoid thing all day long before I would have done this crazy stuff. Am I right?
Yep.
Question. Guess why I was able to do that little trapezoid trick?
Is this a straight line?
Because it's a straight line. Is this a straight line? That's why you need calculus. Soon as that x becomes x squared, or x to the third, or x to the fourth, or sine x, or e to the x, or natural log of x, guess what falls down? All of this geometric stuff goes away, and that's what they were struggling with thousands of years ago. Well, I shouldn't say thousands of years ago, 4,000 of years, until about 300 years ago when a guy by the name of Newton and Leibniz kind of put all this stuff together. Now, guys, this is my last example. I'm not going to complete all of it unless you want me to. I'm just going to get it started. In fact, I'm going to ask you to start it. Okay, and I'm going to give you I'll give you the answer right now. The answer to this problem is 38 over 3. I'm telling you the exact area under this curve from 0 to 2 is 38 over 3. And I'm telling you right now, you can't do a geometry trick like I did with the trapezoid. So here's what I'd like you to do. I'd like you to write the formula. I'd like you to tell me what delta x is. I'd like you to tell me what c sub I is. And then I want you to write the limit thing, blah, 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 with all of that stuff plugged into it. Don't work it out. I'm not asking you to do all the work. I just want you to do the formula that I gave you, the delta x, find the c sub I, and then write the formula with all that stuff substituted in it, and then just stop there.
What did you say the answer?
38 over 3. Okay, virtual guys, as I'm finishing up here, I just put a comment in the chat there, which is a link to my exit slip. I would really appreciate if you would do that exit slip. That gives me a little bit feedback on terms of where you're at with some of this stuff. So if you would do that, I'm going to talk a little bit about this problem, but we're almost at the 60-minute mark, and then I will let you go, okay? So, well, I think I'm just going to write some things down here. So hopefully you can say, yeah, I did it right, okay? So here are the answers. The formula is area equals the limit as n goes to infinity, sigma I going from 1 to n of f of c sub I times delta x. This is the main formula for finding using the limit process to calculate the exact area under the curve. In this particular case, delta x is going to be 2 over n, because you would do 2 minus 0 divided by n, so that's 2 over n. C sub I is just going to be 2 over n I for the sakes of what we're going to do so far in this class. So then our formula is going to become the area is equal to the limit as n goes to infinity, sigma I going from 1 to n. Now here's our function. It's x squared plus 5. So that's going to be 2 over ni squared. That's the x, right? 2 over ni squared, because it's squared, plus 5 times 2 over n. This is all I wanted you to do right now. I'm telling you, once you work this out, that will be the final answer. We are right at about 60 minutes, though. So virtual students, you are, first of all, you're more than welcome to stay. I will keep it on here as long as you need me to for the next 30 minutes if you need. I'll be glad to work this out if you guys want to see it. But the main ideas that I wanted you to get today was sigma notation and this idea of calculating the exact area under a curve. And I know this was tough. I told you this was going to be a tough lesson. And that bell marks 60 minutes. So I'm going to stop recording.